For example, programs which run on your as apps on your phone and send data over to a bunch of machines located around the world from the cloud. And software, building software like this is a complex undertaking. Lots of moving parts, lots of things that can go wrong, lots of things that need to be accounted for, and lots of potential surprises that can occur because of bugs, because of misdesign. So problems with implementation, problems with the design. In other words, did you plan to do the right thing versus did you get that when you actually went to implement it, did you make some silly mistake like a typo? And this complexity in software development is arguably, certainly it's one of the biggest factors that leads companies to fail. That leads one company to eat the lunch of another company. It's the fact that they can handle this complexity. It's the fact that they can more effectively build a large-scale, robust system, a system that's less subject to crashing, less subject to losing people's data than another company. So Gmail is very, very popular and ascendant compared to Hotmail, in part because Gmail scaled effectively. It had a more clean system that was faster and less error-prone than Hotmail. Hotmail would sometimes lose mail, it was awkward ways, it was slow to use sometimes, and sometimes Yahoo Mail suffers from the same things relative to Gmail. So, one of the big factors that allows you to succeed in a competitive environment is how well you can manage this complexity, but how well you can avoid a program just blowing up in your face and something that you thought would be done in a month taking a year instead. And if you think I'm exaggerating, I'm not. One of the old adages, when I was your age, probably think that I only used ones and zeros back then. Right? That's all we had, ones and zeros. And you probably look at someone like Grant Test that he said when he was young, all he had was zeros. It's not true. We had twos as well, So, we got to use a ternary. No, nothing like that. So the truth is, when I was your age, it used to be said if you promised some amount of time, say 7 days, to deliver a software project, what you should do to figure out the real amount of time to deliver this project or this successful working system, whatever. If I said I can do it in 7 days, what you should do is double that, 14 days, add 15 days, and scale up to the next largest unit. In other words, go from weeks to months. Or go from days to weeks. Now, we've learned something from that point. And it's not just about, hexadecimal. It's not just about going beyond ones and zeros. But no, we've learned something from that point about how to do this more effectively. And those who take my course 371 will learn some of the broader ways we can, even in a large project, contain this complexity. And one of the keys to it that will be emphasized in 370 and 371 is incremental delivery. So you do it in pieces. You don't have the big bang where you say, 7 days from now we're going to deliver, the whole system. Instead, you do it in a very incremental way. You add things in, you test, you develop confidence, you get user feedback, and you sort of do it piece by piece by piece. But the fact is, the complexity of software development retains its central place as the limiting factor, the limiting differentiator from success and failure in many areas of software. Okay. And I have noted the critical role of modularity in helping us deal with this complexity before. Why is that complexity helps, modularity helps us deal with complexity? How does modularity help us? The ability to divide up the system into pieces pieces that are sometimes interchangeable, can be replaced by another one. How does that help? Yeah.
Yeah, the way to think about parts, it doesn't seem like the entire system as a whole, but it lets you get to deal with it.
Good, good. And so having separate parts means I can do what with those parts, for example? I could test them individually. I could assign them to different people to develop, for example. I could maybe replace one part without having to replace all the others. Okay, so modularity is absolutely central here, allows us to divide, conquer, means to reuse. We can reuse those parts in other contexts. One of the key things that comes up in software is what's called separation of concerns. And you'll hear probably more about this in later classes, certainly if you want. Separation of concerns. So if we have a big system, a system that maybe does stock trades or something like that, what are different sort of types of functionality that a system like this, different pieces of a system might deal with? So if we think about a stock trading system, it's not a monolithic whole. It shouldn't be thought of as a monolithic whole. It's kind of different domains within it, different concerns within different areas of this system. What's one thing that might be of concern if you have a stock trading system used by brokers in their offices? Yeah, okay, so there's a networking side. So you want to guarantee perhaps secure networking and timely networking. What's another component?
You need a system to update stock at a time of
Okay, yeah, so you need sort of data feeds, sort of a whole data sort of side of it to be able to get the data on the servers. What's another thing? A user interface. You want to be able to have a user interface. Maybe it's a single user interface on the broker's desktop or on a user at home's desktop. Maybe it's a web interface and a desktop interface. Maybe it's a mobile interface additionally. There's a whole bunch of sort of UI-related issues for potentially different UI platforms. And then there's some things that are often called business logic, which is kind of an odd name for it. After all, this comes up in other domains as well, not just business. I mean, if you're running a system for a charity, but business logic, we call it. Business logic has to do with sort of the rules of what's allowed and kind of what happens under what circumstances. So you can't sell more stocks than you have, and if you sell the stock, then it has to try to put it out on the market and see if there's market clearing and get money back and squirrel away. You should never be given money to a stock if it wasn't for a stock that was an individual certificate of a stock that wasn't sold, for example. They go together. Either you sell it and you get the money, or neither happens, but it's a mixture. So there's this thing called business logic. And basically all these things are different. They evolve in different ways. So, more companies come online, and there's sort of both data layer issues, and there's new tickers involved, etc. And then up here on the UI, you have evolution because new devices come out with new form factors, tablets, etc. And you end up changing things up here. And in a well-crafted system, folks, these are separated out. They're also separated out because different people work on different ones of these. This may sound odd. I know, at your level, you may not have an idea of kind of how to understand all the different responsibilities that are out there. There's great job ads that you folks are going to be able to respond to with your computer science education. There's fantastic jobs, but they are different sorts of jobs. There's people who are system administrators that deal with, database administrators. They specialize their whole lives in database administration. There's people who are database programmers and know how to optimize queries and, how to do really sophisticated stored procedures and have triggering mechanisms, etc. There are people who are network engineers that really sweat this level and how to guarantee security, etc. There's people who specialize in business logic for certain domains. They kind of know how things work in the stock business, and they can capture that. And there's people in UI who specialize in UI, specialize in Ajax, so they specialize in programming on Android devices for Android UIs or what have you. So there's different types of people at each of these who specialize in each of these areas. And separating these things out into different parts of the code base means you can have different people working in those different areas, and guess what? You're dealing with sort of Tower of Babel. It's not quite as bad as that, but you have different languages used in each of these areas. Down here you might use SQL, for example. There's a whole bunch of different network protocols, business logic. You might use Java Enterprise Edition for some business logic, or WebSphere. You might use languages, in some cases like Scala or what have you. And up here in the UI, you might be using JavaScript and JSON to sort of communicate to the UI, etc. So there's different languages. There's different domains. So we separate out a system. It's not a monolith. It's not one big chunk. It's divided into pieces. And often we talk about 3-tier or 4-tier systems, separation of data, separation of business logic, separation of UI, and sometimes there's some transport components in here, other components we talk about an n-tier system. So when we talk about separation of concerns, this is actually really, really valuable. We divide the pieces of our system up so that we can use different technologies, such as languages, such as resident coding data, different people working on those technologies. And so, if I'm working on business logic, I don't have to look at all the gory details of UI, and I don't have to be bothered, ladies and gentlemen, if the UI changes. Business logic just works. I don't have to be bothered if the data side changes. If you go from, DB2 to Oracle, or you go use a NoSQL database strategy, I don't have to worry about it. That's your business. As long as your contracts are still observed, I'll depend on your contracts, and you do whatever you want. Just like you don't particularly care how FedEx is organized internally. All you care about is that if you bring the package by this time, it is guaranteed to be delivered by the same time. You don't have to know all the vagaries of how they ship, and whether they have 2 planes to the Saskatoon airport or 1. That's their business. Divide and conquer, ladies and gentlemen. Okay? So we have these different components of the system that are divided up and that are held responsible for different people. And this sort of benefits across the span. And I would note, particularly per the gentleman back there, it helps testing a great deal. Okay? Okay, so this is where we start getting closer to motivating this issue of separation of interface. So it turns out that to accomplish modularity, to make sure that it's not all just one hairball, it's not all just one mess, where every change, one place changes everything without the system. That is a recipe for madness, as I think I quoted to you before. Broaden my playlist, but in King Lear, you say that way lies madness, and so it is with the hairball type system. You are dead in the water if you have a medium to large scale system where a change in one place just ripples through to change in everything. You're hosed. That's it. Game over. You're not going to be able to evolve that system. It's just going to be a huge effort. If I make the slightest changes here, and all the other 50 developers in the project have to go and fix something up, you might as well push off. And that's what systems sometimes gravitate towards, and that's perhaps the main thing that helps keep it modular, keep it decoupled, is abstraction, hiding details. Okay? So that I don't depend on how you implemented something, I depend just on your contract. And you can change how you implement it as you see fit, as long as you keep the same contract. Okay. So this is hiding details. Hiding details in the implementation. Just So that I'm only counting as a potential user of your system on PC. Okay. So here, we're using what's called abstraction, hiding details, and we're treating things that differ in their details, say differ in their implementations, basically as all being adequate, all being sort of the same from the point of view of the contracts provided. So we know we may have a contract for us to sort these data, and we can do so as we see fit with bubble sort or AX sort or heap sort or merge sort or whatever, as long as those contracts are observed. In other words, there's commonality, and we provide the interface that captures the contract, and we allow 1,000 flowers to bloom in terms of how it's implemented. Okay? Now, there's two primary means to doing this that we deal with in 214. The first is what we call abstraction by parameterization. Here, we have some thing that we want to accomplish. We could do so in many specific pieces. For example, we could have a count male and a count female function that counts the number of males, counts the number of females. But we could do better by creating a single function, and it takes a parameter, say the sex to count. In this case, it's any non-small set. And it counts the number of ones of that sex. So instead of having two that are very specialized, we have one that achieves generality by taking an argument. It is able to take in this argument and deal with this broader set of cases, some for one sex, some for the other, internally. Okay. So this is one way that we abstract within our programs. We create parameters, and those parameters hide some of the details that would otherwise require sort of several calls. But that's not the main one I want to talk about today. The main one is this abstraction by specification. Okay. Incidentally, this first one, we strive for it. So whenever you can see an opportunity like this to bring it up to a higher level, have a higher level function that does this sort of thing, it's often a great opportunity. You'll simplify your code base. But today what we're going to be talking about is abstraction by specification. So here, we ignore the implementation details. We just say, we will consider things the same as long as they observe the same contract. Okay? I'm okay with me calling your code. You can choose whatever implementation of that code you want. You could choose your sort algorithm, you could choose your algorithm to perform the square root, as long as I know what you're promising me. What you're promising me, you deal with the how. Okay? So this is abstraction by specification. Here, I need a contract. I need a specification that tells me what I can count on and tells you what you're, by extension, not allowed to change, not allowed to give up. And then by extension, what you are allowed to change is the opposite. Okay. So I think I'll go light on this abstraction by parameterization. It turns out it's a very important thing. Here, let's talk about abstraction from specification. So the main thing that is going to allow this to happen is, number one, separation of interface and implementation. So there's some separation of what I see in terms of the promises you make versus the actual details of the code. So the code that you put in place to implement your square root or your sort may be hidden from me. It's often your .c file that I never see. Or it's in your implementation of your class that I never see. All I see is signature, something that says, like, okay, square root takes a value and it takes a tolerance, it returns a value, and some promise, often in English, that states what promise, there's a natural language. Okay? Here, you deal with the implementation, you tell me what I can count on. You tell me about the contract. Okay. So benefits of this are are ones that I've stressed here. One is separation of implementation. You can work on your thing, I can work on mine. I can build my code, which depends on your thing, even before you've actually built your code. Because I know what it is you're going to be promising, and I don't need your code quite yet, so I'm going to build up my code, and maybe I'll call a so-called stub here, something that's just a transitionary thing that's going to disappear until your code is written. And then I call your code. So you can work on these different components. And modifiability. Because you haven't promised me what sort routine you use or what way you compute the square root, you can change that as you see fit. Because I'm not counting on it. You know that I'm not counting on the vagaries that you're using bubble sort, and if you change your bubble sort to a quick sort, it breaks my code. Okay, because you haven't promised that. Okay. One of the big motivations for this is the fact that code does evolve. We might not change, the routine used for sort incredibly much, but we might as the volume of data goes up. Things like UIs evolve a lot. They evolve very quickly. The data in some systems will evolve quite a bit. In other cases, it will be infrequent. So here, often what we do is we carve off as separate functions, otherwise parts of classes, things that we anticipate changing frequently. So if you want the ability to change your square root routine, you carve it off into its own function. You just provide me with the .h file, not the .c file, and then you can change it very quickly as needed, as long as you make clear your promises in that .h file. So let's consider a little case. Again, kind of abstract, so let's consider a case. Okay, so here we have two routines, ingloriously named, foo and bar, and they are using a bubble sort routine. But in addition to using this bubble sort routine, they are counting on some particular feature of the bubble sort, which is that if there are ties, that the rearranging of things leaves them in order. That may sound odd, but sometimes when we're sorting by a certain value, it carries other information with it. And it matters whether ties are retained in the same order or different orders. So maybe what we're sorting is numbers, like 3, 5, etc., but it's carrying some other information with it that happens to be the person's name or their policy number or what have you. And it may matter that the ties are handled in the same order. Okay. So here we have two uses of this. Now, let's suppose, ladies and gentlemen, that we wanted to change this. We want to change from bubble sort, which is just taking too long, to quick sort. So, as the name suggests, quicker. It actually goes from being, for those who are interested in these things, as the number of items n rises that we're sorting. If we have a bubble sort, it rises as, anyone know? Proportional to n squared. And if it's a quick sort, it's proportional to n log n. And ln n, or to be clear about it, n log n, okay? Rises proportional to that. That may not seem like a huge difference. But if you're dealing with n's in the millions, there's a big difference, and even in the tens of thousands, or something like that. Let's say n is 1,000. We're dealing with 1,000,000 versus, let's suppose this is base 10 log. If n is 1,000, we're dealing with 1,000,000 for n squared. And what are we dealing with here? So we're dealing with 1,000 times 3 log base 10 of 1,000. So 3,000 versus 1,000,000. Is that a big difference? Yeah, it's a big difference. This is the difference that can bring machines to their knees. That can cause your web connection to suddenly time out or something like that. So suppose we wanted to evolve this from bubble sort. Suppose we're getting into the big time, folks, and we're having lots and lots of people add listings onto our real estate site or onto our used bookstore or whatever it is that we're maintaining. So we need to go upgrade from a bubble sort, which is easy to write late at night, to a quick sort. Where would we have to change things? Here. Right now. Well, in both places. We change it one, change it the other. So that's okay, but it's often tedious. We forgot to do it. It's not. It leads to an unnecessarily bloated code base. It may be that different people are in charge of these, and you have to kind of bug someone else to change the other one, or what have you. So if there's a change, we may have to change it at two places. So one way we deal with this, of course, is the abstract calculus. So maybe in the first case, we were sorting prices, and then we were sorting in the other cases ages. And we realized, wait a minute, we don't have to do two different places. We don't have to have different bubble sorts, one for prices, one for ages. We can use abstraction by parameterization. So we can have one routine that just takes in double values, double precision values, and it sorts accordingly. And maybe it returns as a return value information on the ordering, the change that was applied. So if we gave it two numbers and it swapped them, maybe we get back 2, 1 to indicate sort of that they're now in different orders. The one that was in the second index is now in the first, and vice versa. Okay? So here we have a single routine. Now, how does this routine help, ladies and gentlemen? Suppose now, so here we could have done it this other way with one bubble sort routine. Now, how would that help if we wanted to upgrade from bubble sort? What's the advantage? Yeah, we only have to change it in a single place. We only have to change it over here in the bubble set, the bubble sort here. But there's a bit of subtlety here. So if we were to change it to quick sort, we might only have to change it there. But one thing we need to be careful about, we just provide this sort routine. The user isn't clear, how our ties handled, for example. When we change from bubble sort to quick sort, all they may know is, well, okay, the sort routine has changed, and now I have to go figure out, is that going to break my code here? Because it hasn't promised in this evolution of sort. It didn't promise, ladies and gentlemen, as to whether or not the same ordering would be maintained for cons as it did originally. And as a result, I might have to do some fix-up over here. In other words, there was no promise made from sort, and so they changed it however they wanted in sort, and I might have to do extra work because I might have been counting on something over here on the left-hand side that's no longer true. So it's true that most of the work only has to be changed in one place. It's true. But there may be some fix-up. This change may have broken these other uses of it. It may have been counting on things that the folks who wrote sort had no idea it was counting on. They didn't know it was counting on something about ties. Wow, you're counting on that elsewhere in the code base? Are you serious? And now it's broken their code. Bad. Ladies and gentlemen, that way lies madness. It's dangerous. If we may be counting on features of someone else's implementation, they have no idea what we're counting on. They have no idea that what seems like a very innocent, in fact, desirable change, that it may break things elsewhere in the code base. They have no knowledge we're counting on that. We may not. What's even worse is we may not have knowledge to even change that. Or we have only vague knowledge they changed something in there to make it faster. And suddenly we find our tests no longer work. When we test foo, we test var, they break. We say, what's going on here? And then we go on and we look. This code used to work. And I'm still calling it sort, but somehow it's not working anymore. Look, you tried the old sort, it works fine. You tried the new sort, it's not working. Oh man. Well, we're using the new sort because it's so much faster, but we got to fix up this code. That just leads to a lot of wasted time. And a lot of unnecessary wasted time. I mean, these folks over here in sort, maybe if they had known that what you were counting on, maybe they would have used a different routine. Maybe they would have used merge sort instead of quick sort. Maybe they would have used ready sort or whatever. They would have chosen a different thing. They could have chosen it very easily if they had known you were counting on it. But there's no promises. There's no indication of what people are counting on here. That, ladies and gentlemen, is a problem. We've dealt with one of the problems. We're no longer having to do this major change in two places, but we may have to do fix-up. And what's worse is that we may not know we have to do fix-up until tests start failing or until users start squawking. So there's a key problem here. How do we define the interface? I mean, right now we have this sort thing, but there's no promises. There's no indication of kind of what's being promised. And that's a problem. That's a problem here. Knowing the name or the type signature, the fact that, we have a square root, it takes a double, returns a double. The fact we have a sort, it takes an array of doubles and returns an array of ints. That doesn't tell us much. It doesn't tell us much. It doesn't tell us what is promised. It doesn't tell us what it does. All it tells us, okay, you give me a number, I'll give you back a number, a floating point number. Well, what do you do? What are the legal floating point numbers I can give you? What are the ranges, legal ranges of those? What are the things you're going to be giving back to me? What characteristics do they have? Those are the things I want to know. But just looking at a signature, it's impoverished, ladies and gentlemen. It's a pale cipher compared to the meaning of what it does. What's its job in life, sort. That requires more specification. Okay, here, if we could only count on the signature or something, and maybe a little bit on its name, the fact that it says sort, we'd be in tremendous trouble. It might do something quite different than we expect. Maybe sort means sort of thing, or something that's giving back. It doesn't actually sort the numbers. We want to have some understanding of what it does. What promises does it give? What invariance does it maintain? What things does it promise? What things can I count on, ladies and gentlemen, associated with sort? If I'm calling this, what can I count on as being the case? Now, one thing I could do in these days of open source software is tempting to think this is a panacea that solves the problem. So I can go peek at sort. Why isn't that an answer? Okay, suppose I can go peek at sort. Oh, I see. It's using that algorithm. I can count on the things that are ties being, not swapped. I can count on them being in the same order. Why doesn't that solve the problem? Takes time. First of all, it's a waste of my time. I've got to go to this code base, dig it up, and look at it. In some cases, I don't have access to that code base. I mean, there are many cases where we're using .NET or we're using some proprietary format, Google or whatever. We can't look at the code. So it doesn't solve it there. But even when I have access to the code, why does that not solve it? It can change it. It doesn't give any guarantee. Okay, so right now or tomorrow they can change it. Breaks my code. Breaks my code. So I can go look right now and see, but there's no insurance. And folks, if you're building systems which you hope to be running for a couple of years, this is a major problem. Things change. The pace of technological change is very high. And you don't want your system just breaking every time so-and-so happens to output a new version of their library or what have you that gets used. Okay, so, what we're looking for here is actually a contract. It's some sort of understanding of what I can count on if I'm using sort, if I'm using square root, what can I count on being the case? And I leave up to you the details of how you observe that contract, just like I leave up to FedEx the examples, the details of how they're going to get my package to the destination in their promised time. What I know is the contract that I got from FedEx. I brought it in by the necessary time that they need to get that package. Say by noon, I bring it in, and it's guaranteed to be in Vancouver by 5 p.m. the next day. That is the contract that I'm counting on, and I'll leave it up to them, which particular driver they use, and which particular plane, whether it's Bob or Sally as the pilot of the plane. That's up to them. I don't want to know. I, shouldn't have to know. As long as they observe that contract, I'll be a happy camper. Okay? Does that make sense to people? Okay, so what are these contracts like? Well, the contracts can be specified in languages. We have in computer science languages which specify contracts, make them precise, like make them automatically checked and so on. And probably in your professional lifetimes, those will be very important. Right now, they are used by a significant number of people. But often these contracts come in the form of text. In this case, English or other natural languages. So we might have something that says, for sort, someone puts down a little comment. This routine sorts the contact values in ascending order, from smallest to largest. After all, before we can say that, right? You don't know whether it was largest to smallest, smallest to largest. Could have tested it, but there was no promise made. Okay, so we sort it in ascending order for each sorted element, and it specifies for each sorted element the index where that element originated. Okay, so index 1, so the returned thing that results from the sort in index 1, which index did that come from originally, etc. And it says, ties, values of the value retain their original order. Okay, so those are promises. This can be tightened up quite a lot, but I'm trying to give you a bit of a flavor of this. So now we have these uses of this sort routine. And we can change from a bubble sort to a quick sort, again, returning the ordering. And this code doesn't break, because they know that it's guaranteed that ties retain their original value. That's part of the agreement. That's part of what is accomplished. They don't have to look at the vagaries of sort. They don't have to have access to the code base, which may be proprietary. They don't need to worry it's going to change as long as this contract is observed. Okay, so how does this benefit people? Well, it benefits users of the abstractions because it specifies guarantees of what they can count on. That's what we've been emphasizing here. So here they're counting on a certain order because they can know with conviction and confidence that their code is counting on features of this which will be maintained in the future. So users are happy. It's less capricious, the situation. They're not going to be broken on the whims of the evolution of something that some libraries are calling. For creators of this abstraction, folks who create sort, it's desirable because they have a clear understanding of what can be modified. Okay? So if they didn't promise something within that contract, they know someone shouldn't be counting on it. No one should be counting on the vagaries of how sort works internally if it's not specified in the contract. So here, both parties are in some sense liberated. Users of abstraction liberated from the nagging, troubling fear that their code is going to break because this other component changes without their knowledge. For the creators of abstraction, they're liberated from the sense that any change they make may make a lot of customers unhappy. Okay? There's also some additional benefits. One is conceptual clarity, that you're eliminating a lot of ambiguity, and not all ambiguity. We're not trying to be perfect here in all cases. It would be great if you could have perfect specifications, and even on going a little distance, you go a long way towards removing uncertainty. And often in these specifications, we have to pay attention to exceptional or boundary conditions. We have to specify, make it very clear, how we're going to handle certain things. For example, that specification we had really should have said something about how we'd handle a case with no elements, for example. This provides early opportunities for detailed design. In other words, often these contracts are done long before the implementation's in place, so you can kind of plan out what's going to work with what in very clear details. And we're going to be talking, probably the next lecture, about this issue of assertions. The idea here is that the contracts provide a clear statement of what I'm counting on, and I should be able to test that directly. Or what promises I'm making, those promises can then be tested. They can be tested with what's called an assertion, which is a way of sort of operationally saying, It's an operational sanity check. It says, are my assumptions valid? Are my assumptions true? So if I'm counting on, for example, receiving, if I say in my contract that foo must take in a pointer p, an integer that's non-null, if that's part of my specification, p must be non-null. I can reasonably then check if p is null. I can check, okay, is that contained? If not, all bets are off about my contract because you haven't met the preconditions. This would be like someone, if FedEx promises that, you know, if you bring your package by 10 a.m. or by noon, they'll deliver it the next day by 5 p.m. to Vancouver, say, and instead you bring the package at, 3 p.m. They're going to say, well, wait a minute, you didn't specify, you're not in accordance with the normal condition. We need to handle this in a different way. You're not subject. My promise doesn't have to hold, and then I have to get it to Vancouver by 5 p.m. the next day. I've got to handle you separately. So we can check these very simply using what are called assertions and handle them as required in a different way. Okay, and there's easier understanding of code. I mean, if you have these specifications, these would be included here in .h files, and you have some understanding of what that code does. It goes well beyond what you get if you just see the signatures. Okay? And in some cases, these can be used for optimization. You know what you can count on, and therefore you can optimizing it more. The thing, again, I want to emphasize is these will help test creation in a big way, because the tests are often testing the promises made by things. In other words, it's testing that if you give it, for example, a legitimate value, it will return a reasonable value, and what will happen if you give it an illegitimate value, for example, what will it do? Will it behave gracefully, for example? Okay. So here we're talking about contracts. We're talking about things that provide these guarantees. They specify what can I count on. Forgive my lax English. I think it's easier to express it that way rather than, it tells me the things on which I can count. Somehow that sounds more confusing to my engineer here. Okay, so with contracts, we use specifications. Specify these contracts. These are often comments, and they specify what this does, what promises it makes. It turns out that there's many levels of contracts. Some of them have to do with the logic, some have to do with performance. I'll say, for example, this routine is guaranteed to return in this amount of time. Guaranteed to not take longer than a certain amount of time, for example. That's something which can be done deliberately. Let me just give you some examples. Unfortunately, most of these are in Java, where the practice has really been strongly encouraged by Sun and more recently acquired by Oracle. And you'll find for quite a few Java libraries some nice comments in place. So for example, here's a routine that's called index string. And the idea behind index string is that it's looking for S1 as a substring of S2. It's looking for S1 within S2. So for example, if we're looking for BC within this string S2 that's ABC, BC, it will return the first case of where it's located. Now, you can imagine, if I don't have those comments there, and I just look at this name, well, either I'm going to guess, or try to remember, or ask someone, or I can go online to try to look up a specification of this sort. And it's good practice to provide the specification directly to the users in Java docs, if you're in Java, or in the form of documentation, or some way that people can very easily gain access to this information. So this is what we're talking about in example contract here. So you'll notice that it's dealing with some awkward cases. So if S1 is the empty string, what happens then? If we're looking for string that has nothing in it. What do we do? Or if S1 appears multiple times in S2, which one do we return? Or if S1, for example, does not occur within S2, then we return -1. Okay? So we'll return, I don't see any case, what's that value? So this is an example of the specification. Absent the specification, again, it's guesswork, hearsay, core memory, or needing to look at code, but that's not often an option, and it provides no guarantee for how that code will evolve. So this is an example of specification. Here's another sort of set of examples that give some suggestions on refining these. So the first is one that's brief. It helps a heck of a lot compared to having nothing at all, but it's a little bit ambiguous. So for example, it says if S1 or S2 is null, throws no pointer exception. So it says, okay, bets are off. If S1 and S2 is null, as far as doing my work, I'm going to throw a null pointer exception. Otherwise, it returns true if S1 is a subset of S2. Otherwise, returns false. Now, this is a little bit of an ambiguous thing. Why do I say it's ambiguous? What case does it not really make clear? Well, are you folks familiar? How many people are taking 260 right now? Okay. Are you folks familiar with the notion of a subset? Okay. There's a further notion of what's called a proper subset. Have you heard about that? So a proper subset, what is that? So if I say A is a proper subset of B, what does that mean? It means A is every element of A is included in B, but A is not as big as B. It must be smaller. There must be at least some element in B that's not in A. Okay? And the problem is that when people use the term subset, often they mean proper subset. They use it colloquially. They say, "Oh, well, that's a subset of that." Undergraduate education is a subset of all education. What they're really saying is it's a proper subset. It's a subcomponent, but it's not all of it. And so this kind of leaves it up in the air. Now, still, that's a lot better than having nothing there at all. Vastly better. But we really want to be more specific, and we want to break down this ambiguity. So we'll say something like I just said. The problem is this is a little bit wordy, and so we might use something that's kind of a good mix. So returns true if S1 is a subset of S2. Other words, returns false. In other words, returns true if every element of S1 is an element of S2. Okay. And what it's making clear there is, if it wasn't obvious enough, if you've got someone who's kind of wondering this is proper subset or regular, they can look to this next line and they'll see actually it's just a regular subset. It's not saying a proper subset. It doesn't say it has to be it can't be all of S2. Okay. So this is an example of a specification. Here's another case. Too cold. Returns true if the temperature is less than or equal to 0 degrees Fahrenheit, otherwise returns false. So that's good. It would be a problem if it didn't say Fahrenheit, because it would depend a lot on who's reading it, and the assumptions that they bring to the table can be problematic. It might help to just emphasize this is the freezing point of water. Excuse me, this reveals the inconsistency. It should say what was really meant in Celsius, actually, and it comes out here, and someone can recognize this as a problem. So this says 0 degrees Fahrenheit, but then it says less than freezing point. And so really it's talking about 0 Celsius, or 32 Fahrenheit. And so that could come out and be more clear to the person who contributes this, so that they correct the specification. If you provide additional details or examples, it may actually point ways the specification could be enhanced. So this would be a legitimate specification, but it turns out that this one helps further bring out kind of what was intended. Now this is an interesting issue. Why is the top one ambiguous? Indeed. So actually in UK, I'm not sure if it is 10 to the 12th there, but in any case, in the UK and in North America, there's a different understanding of what billion is, what it means. And here it's making clear the particular meaning that's in place. And I don't remember the details of it. Someone could probably look it up right now on the phone and tell me. But the issue is that billion means actually something different. So again, if you put in a bit of additional information or an example, it often helps these things become less problematic. Now, what I want to emphasize here is you'll find different styles of specifications. And you'll notice some of them are more operational. They specify more of the how things are done, and some focus more on the what. So an example would be sort of search here. Okay, we have an array, and we have some array of integers. We have some value. We're going to search for the array, and it's going to return the index of that value in the array if it's found in the array. Otherwise, it's going to signal exception. Have you people heard about exception? Okay. Have they been covered in 270 yet? Yeah. Okay. So here, search. It specifies how it handles the case of A being null. Fine. And then it says it returns the first I such as this is true. So that's specifying the what. Saying essentially, I return for this the most common case, I return the I such that A of I equals X. This is the value. Okay? The top one, on the other hand, has a different approach. It specifies more of the what. That it's looking at A0, A1, A2 in turn, and returns the index the first one that's equal to X. Okay? You'll notice that that's actually much more specific. And it actually does resolve one ambiguity that is optional. Let's put it this way. It resolves an ambiguity. It comes down on one side of, it provides extra guarantees. Let's put it that way. What extra guarantee is provided at the top that's not provided at the bottom? Yeah, you know it's a linear search. And you know the one that it's going to be the I that's returned. If there's multiple cases where X appears in A, the I that will be returned, if they are guaranteed to be the first. In this one, is it guaranteed to be the first? No, it's not guaranteed. Now, you may wonder, so is the top one therefore better than the lower one? Turns out, not necessarily. There may be cases where you do want to provide extra guarantees, but the top one also ties the hands of the developers. Why do I say it ties the hands of the developers?
You're doing exactly what you said in the how, you're kind of breaking it down.
Yeah, and so up there, the only option is a linear search. Maybe you want to do something more sophisticated, or maybe you can, obviously if this were, for example, return, if this were taking in something that's guaranteed to be a sorted value, something that's already sorted, doing a linear search is wasteful. You might do a binary search and come up with it much quicker, and we might not want to make this guarantee. So the top one does tie the hands of the developers. It's a perfectly legitimate specification. Don't get me wrong. Both of these are legitimate specifications. Just the top one provides more guarantees, The bottom one doesn't provide more guarantees. And so a user is using this bottom line based on the specification shouldn't be counting on the I being returned always being first. It's not promised. Therefore, you shouldn't count on it. Okay? The top one does provide this extra guarantee, but at the cost of limiting the options for the algorithms used. Okay? Does that make sense to people? So, I'm not saying one is better than the other, but just realize that there are trade-offs in terms of how much you promise. You know, FedEx, for example, could make extra promises that, for example, the package that you give to them by 2 p.m. to go to Regina, they're going to guarantee that it's flown there. And maybe they want to make that promise. Maybe they don't want to make that promise. Maybe they want to leave open the option that it will be driven by hot rod to Regina. Or, you know, it will be driven by hot rod to Winnipeg, or shot in a ballistic cannon, or something like that. And they want to leave open that possibility, in which case promising extra is not something they want to do. This is sort of a tension. You know, you can promise more, and then you have less flexibility as a developer. You can promise less, but you might not be as useful as you might have been if you could specify more information for just certain types of users with certain interests. So if there is a user who's keenly interested in knowing, is it the first one in order or not, you know, they might prefer one like this rather than like that. Okay? Okay. So all this becomes very, very important for test case creation. I'd like to go through a little final example that illustrates this. So what does this code do? It's code NR. Suppose you were given this code first day of your professional life. NR. I want you to test this code. Or I want you to look, is this code correct? So, what is this? Well, it's pretty opaque. Maybe you can trace through it. So let's see, there's some sort of thing, and it keeps this R, and then it divides. Okay, so it divides one argument by this thing R, which is half the argument, and then it's this loop, and it's looking at R and B. You know, you can spend a while, you can spend hours looking at this, and finally, you might actually come to realize that this is actually a square root to you. This is what's called the Newton-Raphson method for computing a square root. It takes two arguments in. One is a double precision value, one is a tolerance, and it returns a double. Now, certainly the code could be improved in terms of the meaningfulness of names. For example, we could name this R thing candidate root, and and then we could have a thing called n divided by candidate root. And basically, we're looking until we're trying to find the value for which we're trying to find if we have n. This number we're trying to take the square root is, we're trying to find the value such that if you divide n by a, it equals a. That's what this whole thing is about. It's bringing a closer and closer to that value. That's really what it's about. But what would help even more to people who use this routine, cleaning up the names and so on, it's great for people who write the routine, to modify it, that's great. And maybe for some of the testing it would be. But what's even more important for the people who use this routine is having a specification of it. And the first part of the specification it has to do with the signature. It says, okay, this takes a double and another double, double cross double, and it gives back a double. Okay? Give it a pair of doubles, your number, the tolerance, and it gives back a double. Well, that's great. But what's more important is it returns the approximate square root, given input, and really, it should really say at tolerance t. And I should explain that more, actually. But it's a good start. So where does this go to get operationalized? Well, typically we put such a thing in a .h file. Okay? So the actual code goes in a .c file. In our .h file, we put in the declaration of the sort that we've seen, and we put in the signature for C like this. Okay? And that allows people to include, to pound include this .h file. So we do a pound include nr.h in quotes if it's in some folder, and we get sort of the angle brackets, the greater than sign, less than sign, greater than sign, if it's in a standard include folder, so that other code knows about our function. So we have other code, so you have some module that you're working on called foo.c, you pound include ours, and you can actually go look at this, and you'll say, oh, okay, it's Newton-Raphson, it returns the square root, etc. Okay? So that's great. We put that there. So the question is this correct now? So suppose they ask you to test it. Well, it turns out that we can now use this type of information in the contract to write a set of test cases. So we're going to be seeing, in fact, next time, to use how we define this so-called assert function. And we're going to say, okay, for example, if we give this an input of 4, that's the one at the top there, and we give it some tolerance t, is the difference between that thing and the actual thing we know to be the square root of 4, namely 2, is it less than t? Does it lie within t of the actual square root? Similarly, we give it for 9, we give it for 7, so we give it for some perfect squares and non-perfect squares. And then eventually we're going to be asking the uncomfortable question, well, what does it do for 0? That awkward case, we should probably ask about 1. What does it do for -7? What does it return back? And we will discover that it does not work. It breaks in this case, in these two cases, in fact. And it breaks for 0 because it's dividing by it here, for example. So these ones should fail, for example. We're going to just use as part of the contract, say it depends on a positive number. So we're going to actually refine the contract in this case based on our testing. We sort of think it through more, oh yeah, this really only works for positive numbers. So we're going to make it as part of our contract. We haven't yet distributed this code to other people. Suppose we've written the code. It hasn't gotten out to other people yet. So we have the luxury of refining the contract before we give it to people. The general thing I want to emphasize here, and I'm going to let you go here in about a minute, is you want to specify a contract. What's the purpose of this routine? At first, you may define a stub for the routine, and typically, in a test harness, we're going to then include a bunch of things, and we then include the Newton-Raphson nr.h, and then something that will test it accordingly. Okay. So we're going to be talking next time about the use of this assertion primitive, and then we're going to go more into this whole process of developing code. Okay? So that's all we have for today. Thank you very much for your patience. Please remember, if you haven't done already, in the next hour, try to provide input on your availability for the exam review session. I will be getting back to you this afternoon. Okay? Check your mail by no later than 5 p.m. about the time. Hi.
I just wondering,
Yeah.
the midterm test.
Yeah.
Is that more like the